Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Suppose now you have a response, time response of this impulse response. For example, call it number A. For example, say impulse response. That is, for example, h of n is impulse response, which is equal to, you remember, we multiplied by transformation t of this, for example, the impulse unit impulse, for example, in this case. And you want, for example, you want to get using the system, which is time invariant system. You end up, for example, getting the linear time invariant system can be shown in this way. So it's going to be a linear time invariant system having your response system, which is h of n is equal to t of impulse response of n in this way. So this is so common, and here we are providing input as a unit step impulse. This is also the unit step impulse of n in this case. So it will look the same way. So if they say, if you are designing a system, you need all these impulse, you need all the linear time invariant. We said the linear time invariants are those ones that have various variables, independent variables that can be that can have different signals at different levels, and therefore it's very good to understand. Suppose if you have multiple signals and to know how to deal with them, so you come up with a very exciting responses in the end. So this is a general system that looks like it. But suppose if you have to get a response for any arbitrary values, so how will it look like? For example, if you have shifting theorem or shifting values from the system, how are you going to deal with them? So in this case, so if you have an input expressed in this way, for example, having x of n as an input, you can end up having this, having a shift k beginning from infinity to infinity of x of k, for example, in this case, having shifted from any time impulse, I mean unit step impulse shifted from any k value that looks like this. So if this, so you are given in discrete form, the value in the discrete form, and you want your value to look like a time arbitrary responses of response y, for example. So the response y system is going to be, you multiply the other t function, which is t of x of n in this case, which will look like, for example, the normal case that we have seen, which is going to be summation of k ranging from negative infinity to infinity of x of k, of course, multiplied by the transformation between these values, for example, x of n minus k, like this. So this is t in between, which is a transformation that we say. So this is a shift theorem that you can see. So this is the resultant of the system. So it can be written properly. For example, we say it's going to be summation from k ranging from negative infinity then to infinity this side of x of k. This is the shift theorem, which is going to be of n minus k on this side. So you can multiply them. If you want to combine them, you can do like this. But this one remains in the middle as a transformation of your. So this is arbitrary value, or if you have any shifting values arbitrary that you have never thought of, that they are incoming inputs. So using the system as time invariant, we can obtain, for example, shift theorem from all those sides. For example, you can have h, that is a response of n minus k in this side, having t transformation of unit step of k like this, and which is also our y, which is a time response that we work in this way. This is generalization of k, which is negative infinity to infinity of x of k, in this case, putting the impulse response of n minus k in this case. So this is very true, and this is a time response using impulse response. So that is number one. Number two, we say, remember, we are talking about the way how the impulse response and convolution sum can be demonstrated by having different input value. So in this case, we have seen how the impulse response can be taken using shifted or arbitrary values, or when you don't have the arbitrary values. So now we are going to talk about the convolution sum. You will not get surprised when you get all these stars that look like multiplication, but they mean convolution. So any value, for example, x of n convolution, they will look like this star. It will look like a star of y, for example, in a response. So this is a convolution. So there is what we call convolution sum. What does it mean to have a convolution sum? It is an operation that is going to unite together the signals from different sources and just coming together as a single signal. So, for example, here, if you have a response, impulse response, having the response value that is having a convolution sum, a convolution of impulse response, the response value. So, in this case, it is the same as saying summation of the other value that we showed, for example, NK shifting, starting from negative infinity to x of k, remember, of h into n minus k. Right. So this is also true if you want to have a convolution sum. So remember, this is what is a convolution. sum, and it is an operation that is going to show the values. So if we have, for example, the input, as we said, the linear time invariant system, having the input here, a linear time invariant system, in this case, is going to have its response system here, but also having some other signals here below. As we say, y of n as a response is going to be x of n convolution sum of this linear response in this side. And of course, the input can be in unit step impulse, or it can be the discrete value signals that can be mentioned like this. So this is very, very important to note any operation that is done by using the linear time invariant system, having the different signals that you can easily determine their output of their systems. So if you want to get the output of the system, which is y, this is going to be a response of the output, then you can easily determine those values. So there are examples. In this case, the examples, we shall just share them through your emails once requested. But also, there are some ways of how you can calculate this one. You can use it by using, if for example they can give you one of these values. Let me give you a small example, and so that you can easily get the meaning of each and every value here. So you can have, for example, x of n, for example, having which is equal to some values here, 1, 2, and 2. You can also have x of n as input. Remember, the other values were x of n, and the other values were also, so this one can be 1, so 1, 1. So these values, you can see, you can even note them, the way how they are arranged, and say, for example, you can say the beginning from, for example, from n0, any value from n0, or n is equal to 1. So you can, starting a value, for example, if I mention the starting value from here, you can say n0 is equal to 1, for example, depending to how you have said. And also, you can have their responding values. For example, if you have y of n, remember, if you can recall very well, the response is going to be this one, then plus h of n, for example, the convolution sum. So this one, don't take this one as a multiple, but also the convolution sum. So this one also can be equivalent, for example, n0, for example, plus n1, depending to how you have mentioned your value. So and also their frequency domain also can be the big N, for example, 0 plus, okay, this was 1, and then big N1. So don't see this star, you believe that it is a multiple signal. So in this case, you can add these numbers and then get the response. So you can have, for example, the big N. You can have, for example, N1 plus N0, which is equal, for example, from the starting value. You can also have the length of x of n, length of x of n, which can be any number. So, for example, if you consider the number, if you add those ones, you can get n at n1, which is equal to 3. For example, the starting value, which is a response time, which means h of n is going to be 3. For example, here it corresponds to n of 1. And your response time is going to be n, for example, n1 plus n2, then minus 1. We're saying n minus 1. So originally they were saying n0 is equal to n1. So which means here is going to be 3 plus 3 minus 1, which is going to be the length of y of n is going to be 5. You see, from the beginning they said n0 equals n1, and the n1 is equal to 3, as you can see. So that is a simple calculation from here, and you can end up having the general form of which is going to be the summation of k equals to infinity to negative infinity of x of k, then times the h of n minus k, from which n k this time k was 1, and see k was 1, and we subtract it and get the information. So that was a very simple example. So we said beginning from n, which was this value, then you can also do some convolution sum from, for example, n is equal to 1, k will be 0 to 1, n is equal to, then you just substitute it from this general form and then come up with the summation of every point, then you add up, then you can get the y of n in the end. So this was a small portion once given these values here. So you can end up getting the answer, the general answer, depending to where the n will stop. So if it is stopping at 5, less than 5, then you calculate up to 4 values. Or if it is stopping at n minus 2, then you can end up getting the values. So that is one example. I mean, one of the examples of how you can calculate the response using this linear time invariant, which is LTI. We can also use the tabulation method. This is wrong method. I mean, it's called convolution sum using the sequences. But also you can use this is a sequence method, sequential method. But also you can end up getting so you will have your answer as y. Okay, from that is a sequence method. You will have your answer as these values. For example, 1, 3. At n is equal to 1, at n is equal to 2, it will be 3. At n is equal to 3, will be 5. At the n is equal to 4, like that. So some of the values will be, so it it will be in this way. So this is the answer after the convolution sum. Yeah. So, but also you can use what we call tabular method. That was the sequential method. But here also, by using tabular method, you make a table. And then the table will look, for example, like how many values. So the values of h, if I can, remember, you can recall very well in this side. It's going to be, for example, the other values from where, for example, you say this is a table. Starting from, for example, from any value, so it's going to be h of n, or x of n to this side, and it's going to be, for example, the table columns this side, 1, 2, 3. Can some have some other values from the other end, maybe at this side. So you put some of the values, for example, you put the values of h, h of n. Remember it was 1. Was it 1, 0? 1, for example, and then the other side remains, for example, in this instance, for example. So this is going to be h of -1, then h of 0, then h of 1 in this case. And here it will maybe can be h of -2 on this side. So these values are x values, for example. So they are going to be x of 0, x of 1, and then x of 2. So the x of n, x of 1. So the y values or the response at y -2, at y -1. This is the response. Y at 0. Then y at 1. So like that. So you are going to multiply, to sum up the values, or to add the values of x, for example, for the first time, it's going to be x of 0 into, so it's going to be x of 0 multiplied by this. Then it's going to multiply, so horizontal by the x value with x of n. Remember they are x of n convolution by h of n, which is going to be y of n. So the response here is going to be h of this. So it is going to be like that. So we will multiply by that. Then multiply by this is going to be x of 0 into h of -1, and then that way. Likewise, so it's going to be x of 0 into h of 0, like that. So it's going to be x of 0 into h of 1. Likewise, then you take this one, you multiply to the other one, like that. X of 1 times this, x of 1. So you multiply this one, the whole system is going to be okay. X of 1 into h of 2, x of 1 into h of -1, into h of -1, -1. So multiplied by this, and then x of 1. I hope you understand. You can even fill all these forms and finish. So then after that you can close the signal. Then you put them. Then you get some of your values. So remember here we don't need it. It's going to be 0, and this side also we don't have some of its value. So you take at any particular point, you substitute your values, then you fill your form in this case. So it is a general form. So this is an example, but suppose if you have, I hope you understand it. So you multiply the other side, you multiply this throughout, and then the other. So suppose if you have more values, it's very easy. You can get the form. So suppose if you have a discrete value of x of n, which is equal to values like 1, 2, 2, and you have okay, this is the values that we used before, and the h of n. So you can see these are the values that we see. We are going to write them down, note them down, and see how these values can be seen. So and we have these values 1, 1. So that was from our example, and we said from the sequential method we got answers like this: 1, 3, 5, 4, 2. So this is the answer that we obtained from the sequential method that we used when getting all this response value. So we want to substitute them in our table and see whether they are matching, and see whether it is true for everyone. So remember, our table looks like this. So it's going to look like this. So remember, we have h of n and x of n, and we have x values here. We have x values here. We are saying this is going to be a response: 1, 2, 3, and 4. So we have the values of this is going to be, the first box is going to be h of 0, then h of 1, then h of 2, for example, this side, then h of 3, because we are having some more values. Then we will have also y0, y of 0, y of 1, that is the response, y of 2, y of 2, and y of 3. That is the response values. So at x0, we are going to close at x0 to h0, which is 1, 1. So x0 to h of 0. So it's going to be 1 times 1. Then x0 to h1 is going to be also 1 times 1. So this value is going to be multiplied the whole system. So, and here nothing else. So at x1 is going to be 2 times 1. It's going to be the other one. 2 times 1, then 2 times 1 again, 2 times 1, then it's 2 times all because they are 1, and then the other one is going to be 0. At x2, those are going to be the cell is going to be 2 times 1 or 2 times 1, 2 times 1, and 0. So at x3, also it's going to be at x3 we don't have x3 there, so it's going to be 0 throughout. Remember, we have x0, x1, and x2. We don't have x3, so that's why we are putting here 0. So the way how, so the first value here, so it's going to be this, and this, and this, and this, and this. So you sum up, you can get 1 times 1, so you sum up, you can get 1 times 1, so you are getting 1. 1 times 1 is 1. So 2 times 1, that is 2 plus 1, this is 3. Then you move to another step. 2 plus 2 plus 1 is going to be 5. Then 2 plus 2 is going to be 4. Then 2 times, this is 2. 2 times 1 is going to be 2, which is our answer here. So you can see we have obtained the same answer using. That was the response time and I mean the impulse response and convolution sum using these methods, using the sequential and the tabular method. But also we can also use the now we are going to see the properties of the convolution sum, the convolution sum properties. So here we are going to talk about the convolution sum method. So property number 1. If, for example, you have x of n, of course, as a discrete value, and you want to using Z transform as usual, you know this is the outcome, the answer. And in this case, we say region of convergence is going to be at R1, for example. So suppose if it was x1, and if it was x2 of n, using Z transform, can get x of 1 big and Z at R, because if you can recall very well. So the convolution sum here is going to be it's going to look like this. So it's the x of 1 of n with convolution sum of x of 2 of n is using Z transform, then it will be big X of n of Z, then Z, okay, X of 2 Z. So it's going to be like this. So in general, it's going to be x of big X of 1 z, then x of 2 z. So if you want, you can put some of the values that you can obtain. So so that was the convolution sum. So if you compute them, suppose if we have a signal, so you can have x of n as a system input, then you put at the using z transform on this side, you can convert them, just getting the signal here, just going in this way, so it would have one and the other. Okay. Let me just write it properly. So suppose if you have an input x of n, that is input to z transform, then you convert it at this level. For example, you just put it here, then you can just get it here. Then you can have at some point here, then you get other inputs of h of x. So in this case, it's going to be big set at this direction, and you can end up getting the inverse z transform of the time response, which will be of yn, response like this one. At this stage, it's going to be big y of z. This is a big x of z, and this is the function that looks like this. So this is okay. So this was supposed to be, or in this form, going to be z transform. That will transfer this method. So to write it properly, you have your z transform on this side. This is convolution sum on this side. Then you can sketch it like this: z transform of h of n, x of n. And then the yield of here is going to be this, and this is going to be h of c, and the resultant is going to be inverse z transform, which is also y of n. So this is the small sketch of this, the computation of convolution sum. Yeah, so the properties of z transform having two convolution signals, I mean having two convolution sum, is going to be following this diagram, and you calculate them using the partial fraction, the division, the wrong division method, the response method. But the convolution property is going to be number one, is going to be commutative. That one we shall discuss in the next session. But we shall begin from this. We are going to end up from these convolution properties and see. We will talk about the commutative property, the associative property, the destructive properties, and by seeing how they behave, and even we also try to see some of the other factors, including the way how we can use correlation. We just discussed the other systems, and so on and so forth. And this one also, we also have some few examples and calculations. So to end up this lecture today, I have to summarize what we discussed. We discussed about the inverse Z transform, of course, just trying to relate them the way how they differ from Z transform. We said that Z transform mainly is for transferring, or converting the discrete time signal to their corresponding frequency signal. And then if you do inverse, then you are trying to bring a frequency to their corresponding discrete time signals. That is number one. We looked at the properties of inverse Z transform. We discussed, we had also some calculations, calculated examples, and now we have ended up with the inverse and the convolution sum. So thank you for listening, and don't forget to subscribe and see, or you will be receiving the notification for these videos. Thank you very much.